Now that we have formed predictions from our hypothesis through deduction, what should we do next?
Take this example. We start with a hypothesis that electronic devices need electricity to work. My toaster is an electronic device, so from these two premises, we can deduce a prediction that electricity is required for my toaster to work.
Then we should conduct experimental tests to see if our prediction is correct.
One way to test our prediction is to unplug the toaster and see whether it works. Our hypothesis is wrong if our experiment shows that electricity is not required for the toaster to work. What should we do then, Curio?
We should return to the beginning to make more observations.
Exactly. But if our experiment shows that the toaster requires electricity, this test has supported our hypothesis. But wait a minute. Just because our hypothesis has been supported by one experimental test doesn't mean we stop there. We can derive even more predictions and check them with additional experiments.
Why should we do so?
It allows us to know more about our hypothesis.
What if I have conducted many experimental tests to support the hypothesis?
Then we can attempt to propose even more general theories. The current hypothesis applies to electronic devices, but can we broaden it to all kinds of devices?
I see. Let's revisit Feynman to see what additional points he would like to make about the scientific method.
Now you see, of course, that with this method we can disprove any definite theory. If you have a definite theory, a real guess from which you can really compute consequences which could be compared to experiment, then in principle we can get rid of any theory. We can always prove any definite theory wrong. Notice, however, we never prove it right. Suppose that you invent a good guess, calculate the consequences, and discover that every consequence that you calculate agrees with experiment. The theory is then right? No, it is simply not proved wrong. Because in the future, there could be a wider range of experiments, you can compute a wider range of consequences, and you may discover then that the thing is wrong. That's why laws like Newton's laws for the motion of planets last such a long time. He guessed the law of gravitation, calculated all the kinds of consequences for the solar system and so on, compared them to experiment, and it took several hundred years before the slight error of the motion of Mercury was developed. During all that time, the theory had been failed to be proved wrong and could be taken to be temporarily right, but it can never be proved right because tomorrow's experiment may succeed in proving what you thought was right wrong. So we never are right, we can only be sure we're wrong.
What has Feynman told us this time?
He said we should compare our predictions with experimental tests as much as possible. This way, we can gain more confidence in the validity of our hypothesis and find room for improvement.
We should also remember that theories can only be falsified but never fully proven. If the experimental results do not agree with our prediction, then our hypothesis must be revised. However, even if our experimental results do agree with the predictions, we can never be 100% sure that the theory is correct.
Although our predictions agree with all our experimental results thus far, there is no guarantee that they will agree with all experimental tests we do in the future.
If, eventually, such discrepancies are detected, we will need to reassess our theories.